All right, welcome everyone. Now we're going to get started on this last chapter for the course, looking at vector calculus. Okay, so we're going to look at some of our information that we've kind of built up throughout this course, right? Dealing with some of the vector operations, building of vectors in general. Then, very briefly, in chapter 13, which we had introduced some of our vector functions, right? Defining a curve in space by a vector valued function, that R of t, which we'll again address. Okay. And then what we dealt with most recently, dealing with some of those multiple integrals, double integrals, triple integrals now in three-dimensional space, over curves, looking at those components put together. So it's a big culmination of what we've been working on, okay? So for today, we're going to look at this introduction to vector fields. All right, so let me share my document, we'll get going. Okay, and so with our vector fields, we'll start off with this definition. All right, so we're going to let D be a set in R2, right? Our two-dimensional coordinate system, right? A plane region, a region on the plane, right? Just two dimensions. Okay. Then a vector field on R2, on that 2D plane, is a function, right? It's a vector value function, f, that assigns to each point in the plane, xy, right, in D, a two-dimensional vector f of xy, right? So what this kind of idea is that in our R2 plane, right, we can take some region or we can take the entire plane as we go through, right? But for this function, f of xy, okay, is going to have some operation, some action associated with our coordinates, right? We're going to do I and j here, some calculation, so that at every point in that region, okay, we can fill this up more. We take our xy coordinate, substitute it in, calculate these components, and we're going to get these vectors, right? We need to go so far in the x direction, so far in the y direction, at each of these different points. And so as we go through, we start to kind of get these kind of ideas about maybe what this function, vector value function, right? So at every point, we get this vector. And we can kind of think of these kind of vector fields, right? Think of this kind of like electric, magnetic field, right? Or a water current. Water, spell that. Water first, then current, right? In a river, in an ocean. These are these little kind of way I kind of physically think of it. These little kind of forces that are acting, that are pushing on a particle in this region, right? So again, thinking like these water currents, if we had, this is a river, okay, and I set my little toy boat in, these are the way the currents are pushing, this is where the direction that we follow, kind of getting into our differential equation discussion in the future, math 32 here at MPC, kind of thinking about, okay, if I was to start here, then this is the direction my boat would be pushed, finding that motion kind of arcing this way, or again, kind of like maybe wind current. We're designing an automobile like the windshield, the way the wind, the force of air is hitting the windshield and kind of creating turbulence curl. Okay. These are these kind of forces that we can feel in space, how strong, right, what the rates are. Because we can also think of, right, this vector field, we can do a gradient vector field as well, where these are the derivatives of our function in different locations, or how quickly something's moving instead of this particular force is acting. Now this kind of rate of change, we can get into that discussion as well. But overall, when we see these vector fields, okay, we have this region over which we're working. We can expand this to 3 dimensions as well, all right? Where in that region, we have these little vectors kind of point us in the direction that either like this force is moving or maybe that our particle is moving, okay? And so kind of getting ahead into the next section, we can imagine if we have some path we're going to follow, right? If we have our wire carrying electricity, carrying current through that magnetic field, okay? As that charged particle is moving along that path, we can measure that kind of force it feels at every moment along the way, okay? Likewise, if we're kind of having our boat traveling, right, thinking about how those currents are pushing the boat, what actions we're going to need to travel to get from the port out to sea, or from out to sea to our particular port to dock our boat, right? Those currents, those forces that we're acting against. This is that field, just like we had our topological maps, those level curves, the elevation climbing, right? Now we have these vector fields, what forces we're going to encounter as we work our way through this space. Okay, and so as I mentioned, we can also work with vector fields in R3, right? 3 dimensions. And we just have our vector field function f as a function of x, y, and z, right? Where we can see maybe we have this function of what force is in the I direction, what's occurring in the j direction, what's happening in the k direction, and again, we can shorten this notation, right? We kind of start to see that action, what's occurring there. And we can start to build these layers of vector fields. And so I'll put on our Canvas page as well a link to a, I think it was a GeoGebra graphing tool, okay, that allows us to graph some of these vector fields, because definitely trying to compute here and draw these little arrows every time is going to be tiresome, painstaking to do, right? But with the book, some of the book examples, right? This is on page 1113, right? There's a problem about matching up. Okay, if this is my vector field function, right? So at every xy point, the vector arrow we draw has components in the I or the x direction, the y component, the y coordinate, the y component is the y plus 2. Or down here, the cosine of the sum, and then there's the x component. So we're kind of imagining building up at the point 0, 0, the vector be 0, 2, right? So x is 0, it's not moving at all, but the y is 2. So we have this vector up 2, no x direction. Then at the point, right, 1, 0, y is still 0, 0, 2, so we get these little base arrows pointing upwards. Okay. And then as we progress, moving to different point, at the point like say 1, 1, y is 1, so the x direction of I is 1, y plus 2 is 1, plus 2 is 3, so we have that vector of 1, 3, so over 1, up 3, at that point 1, 1. So, and again, stating it as compared to computing it, a little bit difficult. But this idea is that we're going to get these little vectors at every point we can compute with, plugging in. So in the end, we get this region with these little vectors, these little forces, these derivatives, and we start to get these gradient fields that a particle will be experiencing as it's moving through that space. Okay, and so depending on those functions, how complex, how short they are, this one's just a constant, never changing. So the same arrow everywhere. Okay, we can start to incorporate, and then in 3 dimensions, what that looks like. Right, again, much more difficult for me to try to draw by hand. That's why I'll lean on some of our graphing tools and textbook examples. All right, seeing how, again, maybe one of these vector functions is going to look, if I take a point right now at x, y, z, when x is 1, y is 1, z is 0, something like that, right? Plugging that point in and think about what that vector looks like. And so we're going to have this kind of entire 3-dimensional space with those little vectors. So again, as we start to travel through that 3-dimensional space, right, travel on a helix or whatever we're doing, travel on our freeway, that wind creeping up and over the overpass, how that wind force, right, or the wind along the wing of a plane, its direction is moving, the force it feels as it goes through. Okay, so getting used to these vector fields is just some tedious calculation for our x and y, our I and j, or later I, j, k directions, but really kind of just boiling it down to these little forces, these little vectors that are acting on, that are kind of guiding us at different points along some path we're going to start to traverse, we're going to start to go through along the way. Okay. All right. So we have that vector field. Let me see anything else we need. Go. All right. I'll leave it at that to get our quick introduction. And again, I'll put on our Canvas page a little graphing tool so you can, play around with some of these functions that are on page 1113, some of these different vector fields, and just look at what graphs of these vector fields can be produced. And imagine, okay, these are the little forces that we feel from an electric field, magnetic field, water currents, how that's going to kind of push, propel us, act against us as we go through different regions in space, different curves in space, going throughout that vector field.